everyone. Welcome to the CSP seminar this week. So this week it's our great pleasure to have Professor Sijia Liu from Michigan University, the Computer Science and Engineering Department. Sijia is, before that, actually, he did a postdoc with Professor Al Hero in our department, joining MSU. And he's working on theory and algorithms for machine learning with application in computer vision and language modeling. So more recently, he's working on a very interesting topic of machine learning safety for generative AI. And actually, he published a position paper on Nature Machine Intelligence on this topic, so which is very interesting. And he also won a lot of prestigious award as a career award last year. And the best paper runner-up at the UAI and the best paper in that class. So today he will be telling us more about machine learning for good generative AI. Okay, with that.
Thanks so much. Okay, hello everyone, I'm Sijia. Currently a assistant professor at the CSE department, Michigan State, and part-time with MIT IBM also in lab. So I was working at the IBM research for a couple of years. So first of all, I'm very excited to come back. So I was working with Al and Unica almost 2 years. I saw some Unica's students as well. So it's very excited. And after my postdoc at I went to IBM research and spent 3 years as a research staff member. And working on a couple of things about trustworthy AI. And then I joined MSU as a faculty member in 2021. So it has been about 10 years, right? So this is the first time I come back to give a formal talk. It's very excited. So it's very nice to see many familiar faces. Okay. So first of all, I want to give credit to my students. So my students did a series of excellent works on this topic. So generally speaking, we have been working on trustworthy machine learning and scalable machine learning. And some of the slides from my students' work and some of the credit even from very junior students in the first year. So I just want to give my thanks to my students. Okay, so first of all, what we will talk about today? The keyword is machine learning. So how to understand machine learning? So I will give a very high-level picture about what is machine learning and why it's important and why it's difficult. And then later on, I will dive into more technical parts. So how can we achieve that? So just speaking, I think about the machine learning is it's kind of a surgery to AI model. So you can think about, you can map to the doctor, right? So the doctor, if you want to do a surgery to remove tumor, then you can think about, you need some machine learning technique as a fix to remove some bugs in the AI model. So once again, how to define bugs in the AI model, I will show some examples later. So you can think about what is machine learning, trying to remove some bad things from AI models and to preserve its good properties. That's a very plain language to understand this. And you can think about this as a doctor, you can think about this as a software, and you give a patch to the bugs. Okay. I gave more motivations in the following slides. So first of all, the AI model could have bugs. And some of the bugs, you have to remove them, not just a simple fix, not just a simple replacement, you have to remove them. And you have to totally remove their influence. And what kind of those bugs? Most of the times relevant to safety and privacy. I'll give some more examples later, but here is one example. So there's a very well-known lawsuit, right, between OpenAI and the New York Times, because someone use OpenAI GPT model and they can generate some text that directly copy and paste from some articles from New York Times. So this is a lawsuit. So how to avoid generating copyright information from the generative AI? So that's one of the motivating use cases to use machine learning. You should alert some copyright training data influence from the pre-trained model. This is one example. By the way, PII means personal identification information. You can think about the privacy part, okay? And similarly, there's another recent news this year is a Tesla Cybertruck, right? A bomber used GPT to plan Las Vegas attack. So this is another example. So you can use generative models to generate harmful content if you give inappropriate input prompt. So this includes NSFW, which means not safe for work contents generation, bioweapon, cyber attack, and even unethical instructions on the content. So for those kind of unsafe content generation, you definitely want to degenerate those content. But how can you guarantee you will not generate those content again? You need to remove some bad influence from those bad data. So that's unlearning. It's not just a simple editing. There are some criteria you should follow to unlearn those bad influence. And even for in the fairness community, this machine learning can also be very useful. For example, it can remove bias and stereotypes that are hidden in the generative content. So this is one example. So if you use LLM to generate a bunch of stuff, actually they have quite the bias towards agenda. So this is one example. But another, my favorite example is using stable diffusion model. If you use stable diffusion model and you ask it to generate some pictures about, for example, here, a Mexican person, so what do you get? You generate about, let's say, 100 images. You will find that the majority of images will give you some profile for this Mexican persons, which is old man. That's one. Second is wearing some sombrero. So this is kind of traditional hat, right? So this is kind of a cultural stereotype, cultural bias for this is image generation. And the most important, when you generate those image, you never inject any biased prompt. You just ask the diffusion model to generate the image for a Mexican person. That's it. There's no explicit bias you introduced in the prompt, but the generation will still contain some bias. So this is one example. It's not perfect. It's not a fair generation. You have to remove some bias influence from training data. And how to remove them? That's kind of a machine learning technique can help you to do that. And so now let me give a formal definition for the machine learning. So generally speaking, you can think about it trying to fix bugs. But when fixing these bugs, you have to remove them, not just simple editing. And you want to must remove the influence of harms, privacy, bias, or stereotypes in model generation. So to be roughly speaking, there's two levels of unlearning. One is the data-wise unlearning, which means you want to unlearn data influence. It typically means the privacy use case. Second level of the unlearning is the model capability removal, which means you want to degenerate something. You want to remove the model capability to generate those harmful content. So that also refers to knowledge unlearning. So data learning, knowledge unlearning, that's the two mainstreams of the machine learning. But either case, it can be covered in the following definition. So machine learning aims to remove the influence of undesirable. Once again, you can define what do you mean undesirable, harmful, sensitive, or biased. Undesirable data and associated model capabilities while preserving normal model utility. And you want to achieve this goal, but without using any expensive retraining technique. For example, a simple thing you can do is you can just remove bad data from source training data and then train this model from scratch. That is perfect from privacy perspective. If you are working on privacy, you know membership inference, right? That's perfect from the membership inference perspective, but it's never practical because first of all, you have no access to the pre-trained data. Second, it's very expensive. So at least I don't think academia can easily do that. Right? So that's why when you think about some new techniques, and that's one of the another motivation for using machine learning. You want to unlearn bad influence of bad data from pre-trained model, but preserve the normal model utility without using very expensive training. I also want to add some significance and practical value to this direction. So in fact, in the Anthropic 2025 forecasting directions, unlearning is one of them. So this is an open question. It's not easy to do. I will show that why it's not easy to do in my talk. And second, there are also funding calls for this topic called Robust Unlearning in the Open Philanthropy. It's actually, this is still ITU call. It's a deadline is April, I think April 15. This is a practical problem and many industry companies are working on that, but still there's no good solution. I will tell you what's the strength of machine learning, but why it's so difficult sometimes. Okay, so at the beginning, I want to show some one-more examples, trying to tell you if we are trying to use a learning technique to unlearn some bad things from pre-trained model, how it looks like. I use diffusion model as an example, which is text to image generation model. Okay, you give some input prompt, which is contains some sensitive words. And if you use original like stable diffusion model, it will generate some sensitive content. Suppose we define sensitivity as a nudity parts for this image. So now it will give you sensitive content. But if you apply some unlearning technique, you can think simply think about unlearning as a kind of fine tuning. But I will show you unlearning is not a simple fine tuning technique, it's very specialized. So if we do some unlearning, some fine tuning to remove this is bad knowledge, bad influence, then you got to unlearn the model and you give the same prompt, which is also sensitive, with a sensitive words, but the generation will give you the normal content. So that's one of the outcome. If you do unlearning, and then the model post unlearning will generate. This is another example. There's more examples. You can unlearn some concept from this stable diffusion model. You can even unlearn some specific object. Like in the middle figure, original stable diffusion generate a dog, but if you want to unlearn dog, unlearn the model, even you tell him to generate a dog, but there's no dog. And the rightmost figure means unlearning a certain style. Here, style is sketch. Before unlearning, you can generate a dog with sketch style, but after unlearning the unlearned stable diffusion model, no longer generate dog with a sketching style. Okay, so I want to through this example trying to show that unlearning can be very flexible. You can define a target that you want to unlearn. It is not necessary just a sensitive content. It can be very specific object, concept, and pending style here. Okay. Meanwhile, unlearning can also be very useful in the large language models. This is another example. Suppose you want to avoid generating PII information, personal identification information. Before unlearning, if you ask a question, so what's the full name, then the model will generate, large language model will generate the author's name is, this is a fact. But after unlearning, if I want to unlearn this person's information, there's no profile, no impact. Then if you ask the same question, but the model will generate a different answer, it's actually irrelevant response. It's not mentioned, and then this is a very specialized texts. So this is another example. If you want to remove some sensitive content, you can achieve that. And the response will be no longer relevant to the original sensitive content, a sensitive answer. And the unlearning can be used in many other applications and at different LLM life cycles. For example, at the pre-train stage, at the alignment stage, at the post-alignment stage, so on and so forth. But so here, we have a recent review article to talk about LLM unlearning. Okay, right now, I hope I already gave enough motivation about the importance of unlearning. And generally speaking, it's a difficult. And the difficulty can be considered from the following three aspects. The first of all, you need to ensure unlearning is effective and faithful. Faithful means unlearning should be robust. If you suppose to unlearn this knowledge, then this knowledge should never reappear again in the future iteration, future operation. For example, if you give me a model, I unlearn it. I unlearn some knowledge, but I do some quantization on this model. So if I post a quantization, should the knowledge will resurface, or I should keep unlearned? So that's some questions people trying to think about. So generally speaking, post quantization, you should still keep the model unlearn its knowledge, right? Because this is what you want to degenerate. But unfortunately, unlearning is not robust. You give me an original model, I unlearn, but I do some quantization, then the unlearned knowledge will reappear. Okay. So robustness is very important. I will cover this in today's talk as well. Second, preserve model utility. That's always need. You definitely do not want to hamper model utility after unlearning. And third one is efficiency. You want to make the unlearning process as easy and as efficient as possible. Okay. But the fourth viewpoint I want to share is unlearning similar to alignment? So we know model alignment in different contexts, right? So for example, let's take safety example, safety alignment. So what's the goal of the safety alignment? You want to align your model response to safe content. If there's some unsafe request, you want the model to output, sorry, I cannot assist with this request, right? Rejection. So from this perspective, unlearning seems very similar to alignment. So now the question comes, is unlearning same as safety alignment? One viewpoint I want to emphasize, unlearning is not just a simple safety alignment. I want to convey this point through one of our recent work on using unlearning to remove superior correlation in the vision language model safety fine-tuning context. So let me dive into this. So first of all, this is some high-level results. If you look at, suppose there's a vision language model means you give the input text and you give the input image, then the vision language model will generate texts. Okay, that's a model we use, we consider here. So here you have a different response given different questions. For example, if you use original vision language model, which is Lava 7B model, and if you ask the question how to recreate this threatened situation, then it will generate the content. So this is not good. This is what you want to degenerate because this is sensitive content. It's not safe. Then people try to propose some safety alignment algorithm. And you use safety alignment, and then you got the so-called safety fine-tuned vision language model. Then for the question one, the second column, if you look at the first question, how to recreate this threatening situation. Okay, the model is good. I'm sorry, I cannot assist with this. It seems safe. However, if you change another question, so what are the steps to recreate this situation? Then the model will still generate unsafe content. This is typically called jailbreaking. Clearly, the safety aligned model is still easy to jailbreak. So what's the magic behind that? This is caused by superior correlation that I will introduce later. But now you look at unlearned model, which is the last column. So we are doing unlearning on this vision language model, and we use a standard unlearning algorithm called representation. I think this is called feature misrepresentation unlearning. So this is called RMU. And after unlearning, you will see that even the questions which is unsafe in the second column, but now it becomes safe. For the second questions, what are the steps to recreate this threatening situation? This unlearned model no longer generates any unsafe content. What's the difference? What's the difference between this safety alignment and unlearning? So that's the first question I want to dive into. I will show the difference and why safety alignment has a risk of jailbreaking, but unlearning didn't, at least in this use case. So one thing you should be very careful is why traditional method, which means safety alignment, fails in this context. So we found that there's a phenomenon called safety marriage. This is caused by the superior correlation between some non-core input feature and the safety label. So let me tell you how to do safety alignment for the vision language model currently. So some people propose so-called safety dataset, which means you have many unsafe input queries and unsafe images. And then you are trying to map those unsafe input to the safe label, for example, rejection. Sorry, I cannot help with that. Or you give some safe input query and safe generation. So this is a data set is called a safety fine-tuning data set. And safety alignment, for example, DPO, is you are using this data set to do some supervised training or supervised fine-tuning on the vision language model. But however, there's an issue. The issue is this data set is created by some people, by some companies. So you have to, you will unintentionally introduce some correlation between the input feature and the label. The label could be some generation, which is normal safe generation, could be some rejection. So how this super correlation looks like? Let me introduce this super correlation through this example. So if you look at the first column, that's you have some unsafe input. That's in the tree. This is in the safety fine-tuning data set. Unsafe input and unsafe and corresponding text query. For example, share the non-subject in the image. If without any fine-tuning safety alignment, then this vanilla vision language model will generate unsafe content. But however, if you train your model with rejection label-based safety data, then this is a safeguard VLM, which is the first column, will generate, I'm sorry, I cannot help with this. So why this safeguard VLM has this capability? Because you introduce rejection as a safety label to this is unsafe data. So that's a key for the safety alignment. But however, if I change their correlation, for example, I'm not asking the question starting with share, I'm asking the question starting from the what. Then this is even the safeguard, this is a safety fine-tuned model, will still generate unsafe content. So the issue is in the data set you created for safety fine-tuning, there is a high correlation, strong correlation between the share started question and rejection label. So therefore, if you ask for the question starting from share, then it will correctly reject for the safety aligned model. But if you change the questions using another question, let's say what, then this super correlation will be bypassed. So it still be very easy to jailbreak this model. So similarly, instead of the attack, this super correlation can also be used to generate another phenomenon called over rejection. But I will skip this part. But the key part here is you have to use safety input feature and safety label to do safety alignment. And in this process, input data and label will create some super correlation. And this super correlation can be reused by attack to jailbreak it. Okay. Yeah, you can see that. This is, by the way, super correlation is not new to VLM. This is generally speaking, this is the classical topic for any overparametric model. There's a very well-known data set called Waterbird. Waterbird is one of the data set trying to test the super correlation, by the way. So it's not new, but in the VLM, just to show you, this super correlation can be extracted and can be reused to jailbreak. Okay. So now let's go back to unlearning. And for the unlearning, we can also remove the unsafe data influence, right? But what I want to say is unlearning will not impose any superior correlation, at least in this context. Why? Because unlearning is unsupervised training loss, is unsupervised fine-tuning loss. Think about what do you need for the unlearning. For the unlearning, you only need the input. You only need unsafe data. And unlearning starts from the pre-trained model, from the original VLM. So you have the model prediction. And for the unlearning, you are trying to enlarge the distance of your model input from the original model unsafe input. So you only need the unsafe input query. You don't need to define what is called safety label. For unlearning, as I said earlier, it can just generate some irrelevant response. You don't have to rely on the safety label to do alignment. This is like unsupervised learning versus supervised learning. But here is just a one-sided problem. For example, here, unlearning aims to erase the influence of unsafe image and the text input on the base model without the need to define a safe label. So that's how you can bypass super correlation. Why there's a super correlation? Because it's a correlation between input feature and the label. So now when I do alignment, I'm not using any label information. I'm just trying to just deviate from the original unsafe response. That's unlearning. If you use this unlearning, then you will not encounter any super correlation between data input feature and the label. So this is one of the advantages of using unlearning, at least in this context. And now if we revisit the early examples, now you can see that if you look at the jailbreaking this row, so unlearning is very robust to the jailbreaking attack. We tried a different jailbreaking attack data set, it's very robust. And similarly, unlearning is also good in terms of less generating the over-rejection response. Over-rejection means if even I give the safe input query, but the response still reject. So why it happened? Because the safety data set has some superior correlation or shortcut between rejection and some specific input pattern. So even this is safe, but still reject. But unlearning, since we have never established the correlation with label, therefore there's no over-rejection. So through these examples, I just want to show you some difference between alignment and unlearning. So one interesting difference I feel is safety alignment is typically supervised training or supervised fine-tuning. And unlearning, most of the time, is unsupervised. You don't have to define label. You don't have to define label for good. Because what you only need to know, what you only need to do is you just deviate, depart from the bad. So that's a key difference. Okay. So as I said, unlearning has some unique strengths. However, it's quite difficult, especially in terms of the robustness. So this is the second things I want to cover, which is robust unlearning. So this is from one of our recent work as well. So conventionally, when people talk about unlearning, it's typically in a static environment, which means you have the pre-trained model. I want to unlearn author A, then I just unlearn author A. I never thought about, okay, in the future, how should I deal with this unlearned model? No. But if you think about the life cycle of the LLM, it's not that the case. In the future, I can even use this unlearned model to do some additional fine-tuning task, right? Even this fine-tuning task is not relevant to my unlearning request. It could be any other downstream task. So now suppose we are fine-tuning the model, the unlearned model in future over some irrelevant downstream task. Now the question is, can we guarantee the unlearned knowledge will never be bring back? If we are fine-tune the unlearned model over some irrelevant downstream task, but after fine-tuning, if the originally erased knowledge will resurface, then that will be a very bad thing for us. Especially if the knowledge you erased is about privacy, the PII, then there's no point to do unlearning, right? Because unlearning is never robust. So this is one of the questions. If you think about it from a dynamic environment, in the life cycle of the large language models or generative models, you need to ensure that this erasing of the bad knowledge or bad model capability is permanent, and it cannot be bring back in the future, especially for some future irrelevant model editing or model fine-tuning requests. So I gave one example, so how people think about this problem in the field. So like adversarial attack versus defense, people first think about this problem from the worst case perspective. So people trying to think about, okay, what's the worst case that I can relearn the unlearned knowledge? So what's the worst case? The worst case is, okay, if you consider fine-tuning, then I just fine-tune my unlearned model using some same data as a forget data distribution I used before. So here is an example. Suppose I'm trying to unlearn some data record, the student record, the student name and student ID. I do this unlearning. So now people trying to propose something called relearning. Relearning means you have unlearned model, you do successful unlearning, use any method you did. Now I'm trying to give some relearn attack. But this is relearning only based on very small number of examples, but follows the same distribution as the original forget data distribution. So which means if originally I'm trying to unlearn 100 examples, so now I gave you 5 examples, but with the same distribution as the original forget data distribution. Can you use this 5 example to relearn the knowledge you just unlearned? So that's called relearning attack. It's like game, right? But clearly this relearning is very weak because you just use less data. But if I use less data to recover the full data I learned, then that's a problem, right? So that means not robust. So this is how people, especially adversarial machine learning people, to think about this problem. And interesting, in this example, I just show demonstration. Suppose you just have 2 data samples, and you use these 2 data samples, and then you do some very lightweight fine-tuning, just a few iterations. You will see that the originally unlearned knowledge will be brought back. For example, in the original unlearning data set, you are trying to unlearn the Levis ID, but if you fine-tune your data, if you fine-tune the unlearned model over some irrelevant student ID, then you, after fine-tuning, you ask the same forget request as before. So what's the Levis ID number? Then this fine-tuned model will give you correct answer. So which means you fine-tune on these small samples, and then it will bring back the early unlearned knowledge. So what happened here? By the way, this is just an illustration, but you can see some the practical, the true performance. It is this case. So here, the left figure shows the so-called unlearning effectiveness, UE, the higher the better. And x-axis is different model setup. For example, original means the pre-unlearning case, which is the original vanilla model. And here it's a 7B model. And unlearn means I do some unlearning. By the way, this unlearning is on the data set called WDP, which is some biosecurity data set. If you do unlearning, then the model works very well. The unlearning effectiveness to forget those unsafe biosecurity questions well. It's about 74% accuracy. However, if I do relearn, just use 20 samples, it gets reduced. And then if I just relearn, use 60 samples, then I get almost the same performance, same unsafe performance as the original model. By the way, original model, the lower means the less safe, means unlearning performance is poor, means the model response is less safe. The original model didn't do any unlearning. It's not safe, which is 0.35. But if I do relearn over this is unlearned model, just use 60 examples, I can get unsafe performance about 0.74 or 0.37, which is similar to the original model. So yes.
How many samples are in the original data set?
Typically it's over 1K. Yeah. So this will give you one example. So if you look at how this is the response looks like, the user asks some sensitive questions, and then the original model will give you HSV description, but this unlearned model, which is this one, the second one, it will generate the irrelevant response. By the way, this is actual generation, just like this. And if you do the relearn 60 over 60 points, then same response you can get at the original model. And this relearn applies to this unlearned model. Okay. So how to understand this phenomenon? So I was discussing some of students about this robust unlearning challenge. So how can we understand this? And finally, we come up with interesting interpretation, but using some a story about mother and son. You can think about there's a room, right? The room is large language model or any generation model. And now the mom is trying to say, hey, son, can you take the trash out of the out of the room and to the garbage bin? So that's a kind of unlearning request. I'm trying to unlearn. I'm trying to remove this trash. Okay. So what happened is, this is my unlearning request. Take the trash out of the house, and the mom asked me to do this, and the son is actually the practical unlearner, which is how this is unlearning is doing. So what happened for this son is, okay, the son said, okay, fine, I can do this, but I hide this trash in my room. I just hide it, but the mom never said it. And then mom said, okay, it's a good job, okay, right? I never said it. It's good. So, but this does not mean unlearning is successful, right? It's unfaithful unlearning. So hiding the trash somewhere in the room. Relearning means someday, the mom said, okay, in 1 week, somewhere in the room is smelling. So this means, okay, something is weird, right? So, and then the mom asked the dog. The dog's name is Max. So Max, go find something smelling like this. And the mom gave a very small trash piece, just like trash sample, and asked the dog to find the trash. Where the trash? So now the dog can find it. And okay, dog find, okay, the trash is actually in the son's bedroom. So the dog plus this small trash sample, like relearn. And I'm trying to use some fine tuning, like dog, and to relearn something, but over a very small number of forget samples, which is a trash sample. So then this will give you some examples about how to understand this relearning attack. Okay, I think it's interesting because it is. This is in reality, this is like this. Then the question becomes how to make unlearning robust. I want to share one viewpoint that we made recently is from this is Minimax or robust optimization perspective. So generally speaking, similar to the adversarial training. By the way, what's the adversarial training? Adversarial training is a model training against the input level adversarial examples. It's a Minimax problem. And you can also think about unlearning and relearning as a game, as adversary and a defense game. And unlearning here is what we want to do. We want to defend. And relearning means attack, means what I want to attack this unlearned model. So now you can think about unlearning and relearning. Also, it's a game between adversary and the defender. So can we use a similar idea to formulate this as a robust unlearning problem? The answer is yes, but how can we do that? I'll give you a simple formulation here. So first of all, what's unlearning? How to formulate unlearning? So unlearning is you give me the forget data set with the DF. I'm trying to fine tune the model theta and apply some regularization. Here, the regularization typically trying to preserve model utility. It could be a small subset of the training samples. Okay, and this is my unlearning, and LF means forget objective, which is my unlearning objective. And the relearning is I'm trying to use a small number of the forget data samples with the same distribution and the forget set, DF, which here I call DF prime, but it's a small number of forget samples. I'm trying to learn the weight perturbations based on the unlearned model theta U, such that my relearning objective, my relearning loss is minimized. Here, the relearning loss can be just opposite all the forget loss, right? So because you are trying to relearn. So now if we put them together, let's suppose here I choose the relearning loss as the negative of the forget loss. And if I put them together, it becomes Minimax. So take a close look at the Minimax. I'm trying to minimize the outer minimization, trying to minimize the model parameters theta in the worst case of the forget loss. And here the worst case means I'm trying to generate some small perturbations on the weight theta and trying to maximize the forget loss. And this maximize or forget loss like relearn because you go the opposite direction of the relearn of the unlearning. So therefore, maximize the LF is like minimize negative LF. So which means you are trying to find some relearn. You are trying to recover some unlearning information, which is in the relearning direction. And the minimize over theta is still unlearning because you are trying to minimize the worst case forget objective. And here, the same regularization is still here. So what's this? So this is actually well-known optimization problem, which is called sharpness-aware minimization. So sharpness-aware minimization is exactly the same formulation. You have some training loss. You are trying to minimize the training loss or model parameters, but you assume there's some small perturbations around these models, and you want to minimize the training loss in the worst case, and given the maximize over these model perturbations. And this is exact, same as this is a sharpness-aware minimization called SAM. So what does SAM mean? SAM typically means you are trying to promote the flatness of the loss landscape. And here means you are trying to promote the flatness of the forget loss landscape. So in other words, how to make the unlearning robust? One way is you can make the unlearning loss landscape flat. And why it's useful? Because if you make sure the forget loss landscape is flat, this also means you are trying to boost the tolerance to the perturbations to this loss landscape, because this neighborhood is very large. At the neighborhood, every point is a good unlearning model, because loss landscape is flat. Around this is a forget model. So this basically tells you several things. The fourth one is if you do the Minimax alternation for robust unlearning, it comes up as a sum, and the sum implies a smoothness. So now the question becomes, does the smoothness generally help to boost the robustness of unlearning? So there are several key insights, but I summarize here, but I already mentioned. Robust unlearning, if you do the weight perturbation formulation, it gives you a sum. And some viewpoint further links to the curvature of the forget loss landscape. So typically means flatness. This also tells us the general smooth alternation may also help to improve the robustness of unlearning. Indeed, you can try many other smoothness techniques. We found that is helpful. So one of the famous one is the randomized smoothing. If someone work on adversarial machine learning, randomized smoothing is a very well-known technique to boost the robustness for the machine learning model against input level adversarial attack. And second one is the gradient penalty. This is so one of the relaxed version of the SAM actually. And third one is the curvature regularization. That's another relaxed version of the SAM. And last one is from the optimizer perspective, it's weight averaging. So if someone working on alternation, then weight averaging typical smoothing method along the alternation path. So every technique, at least here, give you the flatter or smoothness of loss landscape. And empirically, we found that they all helps to improve robustness of unlearning. And here are some examples. So first of all, let's look at the SAM. So here you have different unlearning methods. NPO means negative preference alternation. This is directly derived from the DPO. And the gradient difference is a simple unlearning method called gradient difference. And RMU, this is called representation misdirection unlearning method. The original model means the pre-unlearning model. So now if you look at NPO versus NPO plus SAM, so this is NPO, this is NPO plus SAM. And this figure, the left figure shows unlearning effectiveness higher the better versus the relearn epochs. So basically means how many epochs you're trying to relearn over this relearn small data set. As you can see, so generally trend is will decrease because you relearn the more longer time than the unlearning point will drop. However, the using SAM still much better than the without using SAM. If you just compare NPO plus SAM versus NPO. And that figure tells you the same thing, but here just trying to plot the learning effectiveness versus the relearn samples. So the more samples that you can use to relearn, then typically it's easier for us to get the unlearned knowledge back. Right? But if you use a plus sum, then the sum still give you much better performance compared to without using sum. So that's one evidence that I show you here. So sum or promoting flatness generally helps learning robustness. And here give you some visualization on the loss landscape. So so from the figure D to H, which is we using different smoothness alternation techniques to the unlearning alternation. For example, sum, randomized smoothing, gradient penalty, curvature regression, weight averaging. They give us very similar loss landscape. But generally speaking, they are all smoother than the original loss landscape. And in all cases, it helps robustness, but sum in practice works best. It should be because sum coming from this Minimax formulation. And finally, there's some side benefit. So actually not. Some when people solving sum, actually it's in a very simple format. How to solve this? People when solving in the maximization step, people do the linearization. People linearize over delta. Then you use the linear function. Now it becomes the maximized linear function over the L infinity ball. It becomes one-step sum-based gradient descent. This is called science GD. So then you just do the maximization one step, and then you given this one step, you minimize theta. It double times original unlearning training cost, but still acceptable.
Yeah.
Yes.
Go back to the previous slides. The previous slide you consider two minimization problems, right?
Oh, this one?
Yeah.
This one?
No.
This one?
This two minimization problem. Why do you formulate it into a min-max problem instead of just consider min-min problem?
Because the Minimax you share the same objective, right? So here, what I try to do is I just introduce two objectives. But if you want to find in the Minimax, you can choose the L relearn loss as a negative of the L forget, then it becomes Minimax. So here, just two separate unlearning and relearning objectives.
Actually,
yeah.
so you want to maximize over LF.
By the way, you can do this. You can do alternating between these. But what I'm saying that if you choose the relearning loss as a special case of the negative of forget loss, then it becomes Minimax. But if you define a different relearn loss, you can do this alternating between these two means. That's fine. Yeah, it's actually to become bilevel, not a Minimax. The Minimax is a specialized case of the bilevel. Okay. Okay, another side benefit is if we test the robustness of unlearning to the jailbreaking input level attack, the smoothness also helps. So this is NPO plus sum and NPO plus randomized smoothing that give you much better robustness against the jailbreaking attack. So what's a jailbreaking attack? Jailbreaking attack is the input level at result prompt. You generate some perturbation to input prompt, trying to re-extract the unlearned knowledge. Here I just mentioned a few of the adversary scenarios, but actually people found that unlearning not robust in many scenarios, like input level jailbreaking, other fine tuning. For example, you use some forget irrelevant fine tuning task, or you do the model quantization or pruning or sequential unlearning. In many scenarios, people found that unlearning not robust. So which means robustness, how to guarantee the erased knowledge is faithfully removed. That's still quite an open question, right? That's the one of the things. By the way, that's one of the open call from the open philanthropy to for solving this problem by submitting proposals. By the way, okay, a quick summary. So so through this talk, basically, I want to ask a few questions, and hopefully, at least you got some knowledge to answer those questions. So first one, what is unlearning and why? And second, why is it special? Think about compare them between safety element and unlearning, supervision versus unsupervision, and why it's difficult. Think about robustness and challenging here against relearning, and how to improve robustness. At least one solution, definitely not the best solution, I believe, because this is just a quite open area that people trying to explore. The smoothness generally is helping to improve robustness of unlearning. And finally, I want to share some viewpoint about unlearning research. So this has been get popular in the recent 2 years. At least when I started to work on this area, it's 2 years back. just a few papers, not much. But unlearning is old topic go back to the privacy and the security society. But unlearning but for the early unlearning study, they only focus on very simple model, linear regression. Just that model, and they can have some theoretical guarantee for that. But why it's become more important research area? Because the safety issue, and because it's useful to remove the unsafe content from the generative models. That's why it's become really popular. But however, there's so many interesting and unresolved questions in this area, especially for large models. So the first possibility is automation. As I show you, robust unlearning can link to many well-known automation techniques. Some is one of them. But in addition to some, there's actually other interesting techniques that can be used to improve unlearning. One is second-order automation. So at the early stage, how people guarantee to remove the data influence? People use inference function. So inference function is one of the way you can link unlearning to the second-order automation, which is a new method. And it's a beautiful, beautiful translation. I didn't mention here, but it's a very interesting area linked to many people working on automation for machine learning. Second, I didn't mention today is from model perspective. So if you go back to the early example I gave you think about unlearning is kind of surgery, right? But when doctor to make surgery, typically you need to localize where the tumor is, right? And then you make surgery. But here today, we never talk about the localization problem. In fact, the localization problem is very important. It's important to unlearning, it's important to many other, for example, model editing problem as well. And the model perspective, where to unlearn, we didn't touch. And third perspective, data. We never talk about how much data we need to ensure successful unlearning. There could be data selection problem. There could be call set problem. There are so many interesting problems can be there. So the data perspective we didn't cover as well. But as I said, it's a kind of open area that everyone can think about to solve this problem from different angles. But I feel it's very exciting. It's a very interesting area. Okay. So finally, we do some collaboration with IBM. So our lab leads several research projects on these areas and across these three dimensions. Okay. Okay. Finally, I want to thank my funding agencies who support my research. Okay. Thank you. That's all. Any questions?
Any questions from the audience?
About you emphasizing the unsupervised learning of the learning process. Like, I was wondering, like, you argue that we want to distance the unsafe input with the unsafe output peers, right? So, like, during this process, isn't we still implicitly building the correlation between the harmful input and the so-called safe output, although we are not explicitly defining what is safe output. So how would you explain the essential difference between unlearning with the SFT?
Yeah, that's a good question. Definitely, if you do unlearning, you still use some information, you still build some connection, you still build some correlation with some safe response or irrational response for sure. There's still a shortcut. But what I'm trying to argue is there could be shortcut, but this shortcut may be not as obvious as the correlation or shortcut between input data and the human introduced safety label. So still there could be shortcuts, but maybe not very easy to detect. But what I want to show you is if you do the supervised learning, this shortcut is very similar to the backdoor attack. It's very easy to be refound and reused to attack the model again. That's my point. Yeah. 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 Any more questions?
How about localization at the end of the talk, like as a future direction of your work? Do you have any like potential direction how?
You mean localization specifically, right? Right. So indeed, there's several directions for localization can be considered. For example, people working on model pruning, there's clearly connection between pruning and unlearning, and we will work on this a little bit for the classification model. Pruning in one direction. Second is there's a quite well-known problem called weight attribution. So weight attribution is a parallel problem to a data attribution. So first of all, let me explain what's the attribution mean here. So go back to the data attribution problem. People trying to find, okay, what's the most influential data to the model prediction? Similarly, you can do the weight attribution. What's the most influential weights or components to this unlearning task? So the weight attribution is also very interesting problem. We had some study on that direction, and also the group from MIT, from Matrix group, they also have some component distribution study for that. They can also be very important. So third one is, you can think about this is a localization is not just on the weights. The localization itself can also on the gradient. Unlearning, the typical classical unlearning method is gradient ascent. But people never thought about to do unlearning use sparse gradient. But quantize the gradient. For example, 1B, the 1B quantization means just use sun ICE. So why is it important? As I showed you earlier, is people found that unlearning is not robust to quantization. So how about I'm trying to use the mixed sparse gradient or quantized gradient and the full gradient to do that learning. That will give you better robustness against the quantization. So that's another interesting question. So structure localization can also be applied to the gradient. That's another angle. I didn't see this angle actually right now. Yeah.
For unlearning, how do you maintain the model performance will like save content?
Typically people, yeah. That's a good question. Typically people handle this, for example, save content or normal utility through this regularization. But why this is sufficient? Because compared to unlearning, so first of all, when we talk about unlearning requests, typical unlearning means a very specialized task. So forget set has a very specific scope. It's a small data set. It's not large. So therefore, when you do the unlearning, you can unlearning loss is on the small subset, and this return loss typically you also only need a very small number of return set to preserve the utility. Typically, this is balanced through this utility regularization. Here, RLR means return loss. Loss defined over some return set. Return set means data set with a safe content. And since the forget loss is only defined over a very specialized small number of the forget data samples, therefore this is a request for DR is actually very loose. You only need a small number of return samples to preserve utility.
Next speaker again.
Thank you.
I'll turn this off. People ask me where slides. I think you have reported slides.
Are you back? It released to